Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today I have a current probe. It came from Micsig. You know, they kind of reached out and asked if I wanted to review one of their probes. I'm like, heck yeah. Teeny channel, but somehow they found me and they sent me this really cool probe. I didn't know they had these even, so they might be a recent release, but they have two versions. I got the little more costly one, but the only difference is the bandwidth. Everything else is the same in the probe. So we're going to open this guy up, take a look at it. Alright, so we're going to open this guy up. Now, by the way, this thing is taped and sealed. It's packaged really well. So hopefully I don't damage something. Now this came from Shenzhen, Micsig. I'm glad it didn't come from another city in China we know about. And the rest of the box is pretty plain Jane. But this is kind of what I expected, because my differential probe came in a box too. I don't even know where I have it. Oh, here it is. Alright, I just had to show you. My differential probe came in one of these nice cases, so I was expecting that thing to be in a nice case. But I guess the wrapping and protection kept the case safe. But you know what? This guy, from the other one I could tell, they're built really well. So I'll bring you over and we're going to do a close-up of this, but yeah, kind of excited about this guy. Pretty cool meter. Pretty nice, right? You can tell from there. This is a nice setup. I mean, look how nice this case is. Okay, so what I just pulled out here looks like a USB cable. So this is powered by USB that your scopes have. The Fluke probe that I'm going to compare this to takes a 9-volt battery. Okay, I'm going to just tell you, the bandwidth on this is 2.5 megahertz. That's nuts. So the Fluke one is by far the next closest price to this, and it's a similar thing. Spec only goes to 100 kilohertz, and that's with accuracy of not too great. Alright guys, pretty excited. Let's bring the camera over here, show a close-up of this guy, and test it. And by the way, this probe, it's kind of neat because they made the probe fairly small compared to, say, like the Fluke one that we're going to compare to. The Fluke, this box, the electronics of this box are built into a handle, so the head size on both of them are similar in size, but on the Fluke, the handle gets a little bit larger, and it's kind of a longer thing, about this long probably, and it has this electronics built into this handle, so it's all one piece. I kind of like this because then you only have to hang this off of your electronics, so you don't have a lot of weight hanging off of whatever you're reading. Sometimes that could be an issue. Alright, I'm going to bring the camera over, we're going to take a close-up look at this guy, and then we're going to do some testing. Okay, and here is our case. It's a nice, strong, sturdy case, by the way. Nice hinges on the back. Now these other kind of clamshells, you kind of hear how they pop in. They're nice, strong clamps, and there we go. Well, if you want to see that, it just has the dates and everything on it. Now look at this. It's cut out nicely for the probe. Okay, here's the USB power cable. Okay. May as well free that from the case, right? There we go. So, and there's our power input. This guy has a nice feel to it. Oh look, it's got another, so I think, I have to look, but I believe my differential probe is set up this way too, so you can, I think, daisy chain products like this if they all need 5 volts. You know what, when I grabbed this the first time, first of all, look at the tension relief on that. Has a nice, this is nice cable, good size cable, but this is a nice jaw. It's kind of got a rough feel here where it's kind of machined, and same here. Look, there's an arrow showing the current flow from plus to minus that way. And that hole is a nice size diameter. Just with this being C cable, you can see I looked up the wire size. It's 13 millimeter hole size, so that can take pretty much any wire gauge you're going to put in there with insulation, I think. I mean, I'm sure someone's got some big old cable that is, say, I can't read that. But, okay, let's see, what does this say? Okay, so I'm bringing you in nice and close so you can see this jaw. Inside, you can see one side of the coil, and look the other side of the coil. That's a pretty good dimension there. There's the other side. There's Micsig there. Okay, and here's the other side. Here's the label. It's category 3, 300 volts. Category 2, 600 volts. And 100 amps DC max, which is equivalent to 70.7 amps AC RMS. It'll do some peak currents higher. I'm going to show you a table of the spec, but like there's a direction right there telling you which direction the current flows through this thing. And you can see the size of this diameter. I can almost get my pinky. I got some big fingers, but anyway, that's 13 millimeters. And I think this is about an inch. Okay, and then I just want to show you the tension relief. I think this is done really nicely, so you can use this a lot without worrying about someday it breaking here. That's nice. And these jaws have a nice spring in them. See that spring? I think this thing's really well designed. This guy is texturized here, so you get a nice grip. It's texturized on this side as well. Okay, I thought I'd show you a close-up of this. Same kind of tension relief here. You got your two different ranges, which the Fluke will have too, by the way. So they compare very closely in a lot of their aspects. Now this has the up and down, where the Fluke has a dial. And this has a zeroing button here, auto zeroing for degaussing. And there's our spec, 2.5 meg, where the A version will be 800 kilohertz, which is still pretty amazing, which still kicks the pants off the Fluke, by the way. And there's our settings there. So our 5-volt input. Again, both cables. This is the cable that goes to the scope. Again, nice tension relief. The end going into the scope. Same kind of termination the scope has. You know, they look very similar. But yeah, nice quality cable. So it's a 50 ohm cable, RG58. It says high quality cable, which it does feel like it is. By the way, the cable on this side is a different cable because it's coming from the meters. So this one, the other one's meant to go to the scope, the 50 ohm. This guy is probably some shielded, maybe triple shielded cable, I'm guessing by the diameter of it. And here's the back side of this. So it does show the CE marking, which, you know, with Micsig I would tend to believe that. That's a real reading. And there's the USB side port. It does come with this little wrap here, so we can wrap the cables up, so that's nice. Alrighty then, what I thought we would do is start by trying to measure the bandwidth to see how good that is, and also at a low current level. So you know what I got here's these leads coming from my function generator, and I can go up to 2.5 meg the bandwidth of this. So what I've done here is I pulled out this 47 ohm resistor, and we'll use that. And what I'll do is I'll just tie it to my generator, okay? And we'll measure the current coming from my generator through that resistor. Okay, so first I'll hit the 0 and wait for it. You'll hear a little beep. Okay, and then using that arrow, I'm going to go from plus to minus that way. So I'll just clip over one of the leads there, and then I'll take. Now this is the differential probe. We'll look at the voltage so we can see how much voltage we have across the resistor and see if we get the right current reading. And then what we'll do is we'll check the bandwidth. low frequency all the way to high frequency. And now low frequency, say down at 1 hertz, that's not anything trivial. So we're going to start at the low frequency. We're going to start at a difficult current measurement, I think. We're in 10 amp range here. Okay, this guy's in the 50X. This is also a Micsig, so hey, makes sense using both. Look how small that differential probe is. Okay, so there we go. We're all set up. USB input. This guy needs USB as well. Hold on a sec. Alright, so I'll just plug this USB into this guy. And we're all powered up. We're ready to test. Zeroed out and everything. Let's go look at the scope. Alright, so what I'm going to do is I've got the horizontal time scale set up for 1 second, because we're going to start at 1 hertz. If you believe that, we're going to start really low frequency. And I've set the measurements up. You know, I've added measurements to channel 3 and 4, gone to the RMS measurement, set that up like that. So that's where these two measurements come from. And so yes, I'm going into channel 3 and 4, by the way. So channel 4 is a differential probe. That's the green one. Channel 3 is a current probe. And so the current probe is set for 50 milliamps per division. And the differential probe 5 volts per division. That's where we're going to start. And we're triggering off channel 4 because the voltage, you know, we expect that to be pretty stable. Rising edge triggering at 0 volts. So we're referenced both channels right in the middle of the screen. So I think we're ready to go. Go ahead and turn on the generator. There's our frequency, 1 hertz. And we're in a roll mode, so it's just rolling across the screen because of the low frequency. We could freeze that if we wanted to. Look at this, the frequency readout less than 2 hertz doesn't give us a frequency. I wonder if it will on the measurement. Let's try that. Measure, add, channel, the green one, channel 4, let's do that. And let's go for frequency. I wonder if it'll do it. I don't do a lot of stuff at 1 hertz. Yeah, it's reading it. Look at that, 1 hertz, and then it goes to 900 millihertz. Yeah, so the measurement works. The frequency counter wants to be above 2 hertz. Alright, so let's just remember this. It's 3.46 volts in that resistor. So if that stays flat, that means the generator is flat. And this current right here is 73.8. And if we take our 3.46 volts and divide by 47 ohms, we get 73.6 milliamps. So that looks pretty darn close, guys. Now, by the way, the spec says that under 10 amps and below, and the setting we're in right now, we could count on a 3% accuracy, which we have that, but it also says plus 50 milliamps, which seems kind of crazy. That must be at the 10 amp range, because down here in the low current range, it seems like it's almost dead on. 73.9, it's, man, it is so close. Okay, now let's go ahead and bring up the frequency. 1 hertz. There's 2 hertz. Oh, now my counter's working. It's right on the cusp. Once it crosses the screen, let's see if it works. Yeah. Well, yep, there you go. Okay, 3 hertz. So if you watch this measurement here, let's zoom in on that since I'm not going to be changing scope settings at this point. Okay, now I've zoomed in. Hopefully you can read those numbers. Now we're going to go up in frequency some more. We're only at 3 hertz, so we're going to, once I get up a little bit, we're going to speed up. But look at that voltage. It's holding pretty darn steady at 73, 74. Now also that'll depend on how many cycles we're taking, how good the accuracy is. So we're at 10 meg record, so yeah, we're at full record length, so we've taken all the data we can. Alright, so 5 hertz, 6. I guess I don't have to count it out because you can see right there what I'm doing. Okay, 10 hertz. Voltage is staying very steady. Okay, let's just go up. Okay, we're at 30 hertz there. Yeah, everything looks great, right? As a matter of fact, I could blow up the increase amplitude just a little bit so we can, well, I can't there, but I can do it on the voltage. Okay, let's continue going up. There's 100 hertz. Yeah, it looks solid, right? So we're going to go to 1 kilohertz. I'm just going to punch it in. Yep, looking pretty darn solid. Let's go to 10K. Okay, there's 10K. Looks pretty darn good, right? Now it's gone up just a little bit, 74.4 and 3.48 volts. Alright, now I'm going to take the dial and just walk up. There's 40K, 50, 60. Look at that, guys. We're going to go up to 100K, okay? There's 100K. We're at 100 kilohertz, and look how solid that is. That is amazing. I love that. The Fluke claims that it's capable of going to 100K, but the tolerance only goes up to 20K. With the Fluke up to 20K, it says it's 12%, and we're looking really good. So we're up to 100K where the Fluke says it's capable of going. I imagine it roll off quite a bit from 20K because it's readable measurements the Fluke calls out. But look at this. Okay, now we're gonna jump up in hundreds of K. So there's 200K. Still a really good reading. Okay, I'm gonna go 500K. Look at that, 500K. 500 kilohertz, 3.51, 77 point, it's jumping around, 77.5 or whatever. So, man, impressive. Okay, let's go to 1 megahertz. I'm impressed. 1 megahertz on this probe that's less than $1,000. Look at that. 73 point, it's kind of bouncing around, you know, 73.5, let's say 3.52, and you can see 1 megahertz here. The impressive thing to me is the wide bands, plus we're under 100 milliamps and we're getting good readings. Okay, we're going to go to 2 meg. Says it's good for 2 megs, right? Now look at that. We're seeing a phase shift. Okay, let me go back to 1 meg. Okay, I didn't notice that. 1 meg, there's a phase shift too. The voltage reading's good, but there is a phase shift. Okay, at 2 meg, the voltage is starting to drop off. So the 2.5 is the bandwidth on that. So let's see. So 52 milliamps would be the 3 dB point. And I think they called it because it looks like we're in a, okay, there's 2.5 meg. You can see it here on the counters. And we're just above the 52. So, wow, they did a good job speccing it, I think. Okay, I'm going to go to 3 meg. There's 3 meg. And we're just below the 3 dB. So this one right here, about 2.8 meg is about the 3 dB point. So, yeah, their spec of 2.5 is good. Now, the thing is, you know, once you start in that 3 dB point, you're also going to get the phase shift. So that's to be, you know, expected. Alright, so let's take some DC measurements. We're going to use this old HP power supply. It can go up to 15 amps. So what we do is just crank up the voltage a little bit. The current's turned down. So once I start turning current up, by the way, this is how you set the current limit on a power supply. So you can just set it for, say, 3 amps right there and be done. But we're going to do that and look at it through the probe, okay? So let's come over and look at the probe. Alright, so let me just scroll over here and let's see if we can set the screen up like that. So now we can monitor the current here and here as well, see how they match up. Current's coming from the plus, and just like the arrow shows, plus minus, it comes up and goes back in. Okay, and we're going to do this up, we're going to do some higher currents first, And then we're going to go to some lower currents, and I'm going to put a multimeter in series so we can kind of compare that to multimeter as well. But the higher currents, there's a range setting, right? The 10 amp, 100 amp setting here on the probe. So we're going to be in this 10 amp position. By the way, let me show you something. When you zero this out, watch the light go on here at 0. And then you hear the beep, and then it goes off. If it beeped like 3 times, like beep, 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 it means it wasn't a good 0. What we want to do is we want to go above 10 amps and show you what this guy does. And then we also want to go to the 100 amp setting and see how accurate it is. Alright, and channel 3 is what we're going to be looking at. It's set the times 10 position right now. But what we want to do is just bring it down to the bottom grid so we can try to get a good reading across the screen. So I'll bring that down where it says -4 in that little window. Okay, hopefully you can read that. And the current probe is, I've got the current setting times 10, and let's go full bandwidth. Okay, let's go ahead and bring the current up. Okay, it's showing 3 amps there, and looks like just slightly above, so maybe I could calibrate my meter, right? Okay, let's go ahead and take it up higher. 6 amps. Now we're going to go off the screen there, so I got to go 2 amps per division. And then right there, you see that? Right over 10 amps. You hear that? Yeah, so that's our warning right there. So, you know what? Let's set it at, let's try this. Let's set this at 6 amps. Okay, this says 6 amps, okay? Now I'm going to go ahead and change the probe for 100 amps per division. And then go to the scope and go to times 100. Okay. Alright, and it's 6.14, something like that. So it's giving slightly higher reading at the 100 amp scale, showing the resolution compared to the 10 amp scale. That's pretty darn good because that is 6.2 maybe. It's kind of bouncing around. That's pretty darn good, I think, for a 100 amp scale to be that accurate down at 6 amps. Let's try zeroing the probe to see if we get a better reading now that we've got it in the 100 amp setting. Pull that out. You can't have any current going in there when you're trying to degauss, right? So hit, now listen for it. There it goes, light goes off, and ready to go again. Alright, I had to change the range here on the scope to 2 amps, or 1 amp per division again. Let me bring that up so we can see it in the screen. Get rid of the menu there. Okay, there's 3. Okay, and 6.03. So you know what? Degaussing worked. It helped get a better reading there. So yeah, whenever you change the ranges on your current probe, I suggest degaussing. Alright, we're going to go to a low current setting in a moment. But while we're set up on our 100 amp scale, let's try a surge current, okay? So what I'm doing is I've maxed this guy out, and we're going to just poke this in here. But what I have to do is go over my scope and hit it on single trigger, okay? And then I'm going to see my triggers right here. By the way, I went to 5 amps per division. So 5 amps, so my trigger set just above that. We should get at least 15, 18 amps. But you know what? There's some caps in here, and it'll be interesting to see how much surge current we get, okay? So it's going to trigger right here in the center. I'm going to move that over here so we can see as much as we can of what happens after the surge hits. So I just lined it up right here. So it's going to trigger on these crosshairs. So we're going to see some rising edge. Maybe I might miss the first part of the edge. I don't know. Let's see what happens. Okay, here we go. Okay, I'm going to unplug it. Alright. Well, look at that. Okay, 5, 10, 15, 20, 25. you know, 28 amps peak. And this thing was, you know, set for continuous current around 15 to, let's see, I wasn't watching, let's see what it did. Okay, 16, 17 amps, 5, 10, 15, so it looks like it's coming there. Let's get, I'm going to change the time base from 20 microseconds. So by the way, that was 20 microseconds, so 20, 40, it took about 40 microseconds to peak out. So let's do that. Wow, look at that. I wonder if that's real. Sometimes you don't know if you catch. Yeah, look at that. I wonder if I caught all that stuff. So this memory is pretty deep. Even though my screen was only set for this, it does catch stuff that you didn't see on your screen. So this could be true. So let's go ahead and single trigger and try that again. Here we go. Yeah, wow, look at that. Now, I'm kind of probably bumping around on here, so that's probably why we're getting this stuff. But yeah, there we go. 5, 10, 15, 20, 25, looks 28 amps maybe. And this is 100 microseconds per division, and that happened in, you know, less than half division. So again, about 40 microseconds probably. So there's an inrush current. That's pretty cool. That's nowhere near as fast as this probe is capable of doing, but that was pretty cool. Alright guys, what I decided to do is start off at 6 amps because we did that 6 amp before when we were comparing this meter to what we saw on the screen. So I've got this set at 6 amps, 604, and look at this. This is a 10 amp. Okay, we got the current going through the probe there, going to the 10 amp range, out of the common, and then back to the power supply, okay? So as you can see, up here, 6 amps, 6 amps, and this guy looks like he's a little bit over. I guess I could calibrate that. It used to be they used to have a little screw here you could calibrate them, but I don't know, maybe I have to go back in here. Alright, now we're in the 100 amp range on this guy still. So what we want to do is I'm going to drop this down to say 1 amp. And let's just see what that 100 amp scale, how accurate it is. So we're going to watch this meter and set that for 1 amp. Okay, just fine tune it there. Okay, there we go. That's pretty darn close to 1 amp, right? Okay, over here, look at that, 1 amp. So that's a 100 amp scale, guys. That's pretty cool. I'm curious. Let's go down to half an amp. I'm going to go to 0.1 amp if I can. This power supply starts getting hard to get down to control the real low currents. Okay, there's, oops. Okay, there's 0.1 amps, and let me get it. Okay, I'm all the way down at 100 milliamps per. That's the smallest scale I can go on the scope setting with that, and I'm seeing about 160 and 120 milliamps. That is impressive, I think. Alright, so you know what? Let's put the probe on 10 amp. Then I got to go back here and set it up on the scope times 10, and then we got to change this down so we can get a reading. There we are, and it's saying about 200 milliamps. So what we got to do is degauss, right? So let's pull it out, degauss the thing. You'll hear it. There we go. Oh, it beeped twice. I think that means it didn't like it. So let's try that again. Okay, that was a single beep. Alright, so what I'm seeing here is about 101, 104, 99. That last digit's kind of moving around. Wonder if I can get another. Okay, it's right around in the low 100s. 103, sometimes 99. If I change my bandwidth a little bit on the scope, I'm down to 50 microseconds. I was running pretty fast before. Now it's right at 100 milliamps. So let's go to 1 millisecond. Let's just see what happens. Okay, that's 1 millisecond. Looks like that's probably a little noise coming from my power supply. So when it was bouncing around, it's probably because it was seeing this high frequency noise. So wow, that's the advantage of a current probe, is even at DC you can see some of this junk that this guy's putting out at those real low current levels. I might need to replace some capacitors in this old power supply to get that to go a little smoother. But yeah, 100 here and 101, 103, pretty nice. I'm pretty impressed. Let's see if we can go a little bit lower. Like I say, it's kind of hard with this power supply, but there we go. Okay. It's a lot of noise. Okay, I'm in 10 milliamp range. I'm kind of maxed out on my scope setting. I'm seeing 15 milliamps here, and I'm seeing about 15 to 17 milliamps here. Now if I, pull this out like this and zoom in, it bounces around because it's got all this noise. I could also go to acquire and change my sample to average, and let's just average 8 readings or even 4. So that's not very much of an average, but there's 4 right there. And we got 15 here, and we're getting about 16, 17 there. So that's at a 10 amp range, and that's just far better than the spec is for this probe. So I think that's pretty impressive. The high frequency, the wide bandwidth of this probe is very impressive. Alright guys, let's try this. There's another thing you can do with these probes. It's kind of overkill for the multimeter, and by the way, this BNC, it's a snug fit on that scope. You can put one of these adapters on. You get a Pomona one, get them on Amazon. I'll put a link down below. They're not very expensive. I think they're just a few bucks, $5 or something. Let's go ahead and put in this meter. Here I'm going to have to break this connection, okay? So we're going to just go right through the probe, right back to the meter, like that, like the power supply. Now the current's going to go up a little bit because now we don't have the burden voltage of the DVM, the digital voltmeter, in the... Okay, so you stick it in right there like that, and here I can stick this in here and keep track of my little plugs. Okay, so then come over here to volts. I think it's millivolt range, and look at that, it's 0.26 milliamps. Well, that's AC. Let's see if that's right. Okay, let's go ahead and bring this current up. The Micsig is in times 10 position, so you have to multiply this by 10. So it's saying 173 milliamps, and it's most likely 1.7 amps. Okay, bring it up a little bit higher. Okay, now we know where the 6 amp setting is. It's just over the 6 amp. So yeah, it's right about there, and it says 600 millivolts, so it's really 6 amps. Alright, so yeah, so you can use these things in a multimeter if you had a question about that. Stick in the millivolt range, and remember to multiply by 10 because of the times 10 sitting on your thing here, or times 100 for that matter, if you're in the 100 amp range. Alright guys, yeah, excuse my handwriting. I just thought I'd show you my notes that I made. The Fluke ADI-110S is what came up. $850 was the standard price on Amazon. $765 is like kind of their sell price. And we're comparing it to the Micsig Cp2100B, which I have, the $599. I think I kept saying $550, but it's $599. And the lower cost one is $399 for 800 kilohertz. Now one thing I've kind of underlined these 3 things. The rise fall time of the Fluke, which kind of speaks to how fast the bandwidth is, it's less than 4 microseconds. Okay, the $399, the 800 kilohertz, is 10 times faster. It's 437 microseconds. And this 2.5 megahertz bandwidth on the one we have is 140 nanoseconds, so it's extremely fast. That's why the wide bandwidth. Now Fluke has the basic accuracy, starts at 3%, it goes to 12 to 15, and other than the bandwidth of the two Micsigs, the rest of the specs are all the same. The basic accuracy of the 10 amp range is the same as the Fluke. The other one, it goes from 4% and then down to 15%. And then on the Fluke, they have this additional error depending on frequency band. And you go 3% just from 1 to 5K. So that makes it not quite as good as a Micsig. And then 12% additional error for 20 kilohertz bandwidth. And then after 20 kilohertz, it's not specified. It says useful information to 100K. I don't know what that really means, useful information. But this guy is spec'd. They don't have this additional error, all this stuff. This guy's much wider bandwidth. So, and it can go 200 amps peak to peak with AC, or 100 amps peak with DC current, and a combination of AC it's 100 amps peak. Where this guy has kind of this breakdown, but I'm going to show you some curves from Micsig that have something similar to this. They'll show the accuracy and with or frequency band, but it's a bit better than the Fluke. Okay, so for the Micsig, this is the A version. This is current rating versus frequency. So 100 amps out to about 30 kilohertz, and then you derate down to this thing. So that's kind of like what Fluke was spelling out on that table. But if you compare this, even the 800 kilohertz version is better. And here's the roll-off. So they're showing at just over 100 kilohertz, 150 kilohertz starts to roll off. The minus 3 dB point is out here, and it shows about 800 kilohertz right there. So they really zoomed in on the roll-off portion. And then here, this is the curves for the B version, what I was showing. So the roll-off comes all the way out here to 1 meg, and then starts to roll off, and 3 dB shows about 3 meg, which is about what we tested. And this is an interesting spec. They're kind of showing the roll-off again as you go up in current, and then it starts to tailor off to 100 amps. But they show this is their spec, the blue one, but the red one is typical. So you can, and I think we were seeing more towards the typical than what the spec was showing. But you know, they're being conservative, it looks like. Instead of showing that curve, they just went inside. But I like that, because we actually did see something closer to the red line. Hey guys, so what do you think of this thing? I'm super impressed. You probably can tell. Hey, before we go any further, I want to talk a little bit more about this. But before we go any further, I just want to say happy 4th of July, happy Independence Day to, you know, all you guys out there, Americans or whatever. Everybody else, happy day. It's a national holiday. A lot of people have the day off. I actually had to work, but I took the time off to do this video. I'm hoping I can get it out before the weekend's over. I was hoping to get, anyway, it always takes me a lot longer to do these than I think it's going to, but we're going to try, okay? So what I also want to say is thank you to Micsig for sending this. They reached out, said, hey, we like your reviews. You want to review a current probe? I didn't know they had it. I have a differential probe that I bought just over a year ago probably. It's been sitting here on the bench. Really like that. And I'm like, you bet. It takes a while to do these videos, and so I really don't want to do them unless I think it's worthwhile, and this was definitely worthwhile. So they asked me which probe, and I told them the most expensive one. And so I picked out this model. They had two of them. The Cp2100B is the 2.5 megahertz. The A is the 800 kilohertz, and that's $400. $600, $400. really good deal for the bandwidth and all the features and the performance you get out of these. From what I can tell, this is going to be awesome. I'm excited to use it in other projects. So when I researched to learn more about this, as I was waiting for it to come, it came pretty fast, but I did a little research, and Google popped up with the Fluke, the 80i-110S, I think is what it is, and that's what I've been comparing this to, because price, you know, this has a 13 millimeter hole, the Fluke has 11.5 or just under 12, and you know, everything seemed to be, you know, same kind of current ranges. The frequency band way different. The Fluke is $850 for 20 kilohertz bandwidth, but it's on sale for $765 on Amazon. $165 more than the $600 version that I have here of Micsig, and that's retail list, you know, suggested retail price. And right now, since it's new, that's what Amazon's showing. But I think I've seen it in other outlets, maybe Banggood, for a bit less. So I'm going to put links down below. Okay, so check out those links. That helps. And by the way, thumbs up for the video if you like it. That really helps. That helps me a lot. Hit the like button. That helps a lot, guys, and appreciate that. And you know what? I've been really happy with this. Now, one thing I want to say about current probes, they're non-invasive. You don't have to open up your circuit, which is going to change the operation of your circuit. Inrush current, right? You put a meter in there or a resistor, you're going to change that. Another thing, safety. You're going around an insulated conductor. If you don't have to be insulated, but you can go around an insulated conductor, and that makes it safe. You know, you can get a meter like the Flirt that I reviewed not long ago, category 5 rated. I trust it, believe it is. Can measure 10 amps. You might be on a 220 volt service and want to read 10 amps through that thing. I'm not going to. I trust the meter. That's just a lot of energy. That's why they have the category ratings. I'd rather have something like this, where I can just go like that around the insulated conductor. You know, usually, a lot of times they're insulated, right? But you go around the conductor, insulated or not, and you don't have to worry about touching anything. I can go in the panel, you know, some high energy circuit. I just feel a lot safer doing it this way. So the other thing I like in comparison to the Fluke, where the electronics and the probe were all built together, well, then you have this long, slender probe, which I think they tried to make it as small as they could, but still, this is so small that it's very easy to stick in and take a current reading on something where that probe might be a little more difficult. I've had cases where I've had multiple probes, like up to, I think, 6 probes, and that gets kind of, you know, kind of packed in there sometimes. Kind of hard to get all the probes up in there. And the other thing is, once you go in there and you've hooked onto something, then you're out taking measurements and you're like, oh shoot, I want to change the range, or what range was I on? You want to double, triple check that thing so you're not taking the wrong readings. Well, something like this where the box is, you know, it's about 3.5 feet away. You can sit there and zero it. You can hit the range buttons. It has manual zero adjust. That's nice. I didn't even play with those. So that's very convenient. The other thing is, it's powered by USB. That's a plus. No 9-volt battery to, you know, drain when you forget to hit the switch. Like I do that sometimes. That's why I have some rechargeable 9-volt batteries around here. Anyway, this guy's about 2.5 feet, and you can plug it in. You got room to move it around on your bench or whatever, so it's a convenient length. If you wanted longer, you could always go BNC to BNC, but this, to me, I think for what I'm doing, is going to be great. You know what else? I like the color scheme. I like the design, the ergonomics. I like everything about this probe. You know, sometimes there's something that you're just kind of nagging at you, but in this case, I just think it's made really well, and I like the gray with the light blue with the white text. I think it just looks nice. I think they did a great job, so thumbs up, Micsig. I'd give you more than 2 thumbs up if I had them, but 2 thumbs up. And by the way, 2 thumbs up for my Patreons. Really appreciate the support, and all you guys for watching the video. 2 thumbs up. So thanks for supporting the channel and all that kind of stuff. And you know what? For an AC DC probe with a wide band, you know, with that kind of current range, and so far the resolution looks really good. We're going to find out in future videos, but right now I gotta say it's a winner. Hey, thanks for watching, guys. We'll see you next time.